Hello class, and welcome to this new section where we're going to be looking at concrete. So far in the building materials and testing module we've looked at aggregate, we've looked at cement, and now we're going to look at a product which is a combination of those two. Concrete is basically a mixture of cement, aggregate and water. So in this section, not lecture, because we're probably going to do this for 2-3 lectures, we're going to look at some of the key considerations for making concrete. There isn't one concrete that is the same as another. We're going to talk about the principles of mixing concrete and placing it. We're also going to talk about how to test unhardened concrete. So unhardened concrete, that's when it's still liquid, it's still a sludge, and we're going to talk about some of those properties. We're then going to talk about the science of hardening. Now, hardening is not what you think. I touched on this when we did cement together. Hardening is not it going from being a sludge to solid. It's a case of it going from being weak to strong. Concrete, even after it's dried and it's gone solid, the chemical reaction of cement turning into strong chemical bonds will go on for many days and months, and I'll show you that later in a graph. The next thing, and from that we're going to talk about the importance of curing. It's not about curing a disease. Curing is a term we use in concrete technology for making sure the concrete stays hydrated. We'll talk about that later too. So, what are the components of concrete? Well, remember, concrete is basically a composite of cement, water and aggregate. Do not confuse cement with concrete. I think in Kurdish, or at least in Arabic, I know that the word cement can be used to mean concrete. They're used interchangeably. They are not the same thing. Cement is a glue that can hold aggregate particles together, and when that happens, then it forms concrete. And water is part of that ingredient. You need that to react with the cement. Now with aggregates, normally we will have two kinds of aggregate. We will have a fine aggregate, something like sand, and then a coarse aggregate, something like crushed rock. Why do we do that? Well, if you remember from our aggregate slides, from our aggregate lectures, we talked about the importance of grading. If you have a well-graded aggregate, then basically you're going to have a stronger concrete. There's going to be fewer voids that will need to be filled with cement. You're not going to end up with big cement water paste voids. Now, obviously getting an aggregate well graded is a little bit tough, and so we tend to go towards gap graded, and so we normally talk about the aggregate that we add to concrete as being fine aggregate, the sand, and coarse aggregate, the crushed rock or the river gravel, and together they form a gap graded aggregate. So let's talk about aggregates for a moment. I had a question last year when I did building materials and testing. They said, "Sir, why don't you just make concrete without aggregates? Why don't you just make it out of cement and water?" And I thought that was a bit of a strange question, but because I think it's a little bit obvious, but I'll try and explain this to you. The aggregate gives body to the concrete, so it can fill voids, it can fill the body, the mold that you're trying to fill. It also reduces shrinkage. Remember what I said about how cement actually shrinks when it dries and goes hard? The same happens when you have cement and concrete. So if you have a higher proportion of aggregate, then it's going to be it's not going to shrink as much. It also affects the economy. The more aggregate you have, the cheaper the concrete will be. If you're making a concrete out of cement, water, and aggregate, what do you think is the most expensive component by volume? Well, it's the cement, isn't it? And so if you have more aggregate, you'll need less cement. Now, the other thing with aggregate, it does actually give strength to the concrete. The cement is holding the aggregate together in a matrix, and that is where the strength is. Cement does not have strength in and of itself. So if you can imagine you had some glue, and I told you to make a figurine out of glue to make a little model man on top of your desk, it's not going to be very strong if you don't mix that glue with sand, with an aggregate, because the glue itself just holds particles together. Sort of like if you can imagine a nail in the wall, that's going to be held to the wall, and if you hang a picture from that nail, there's going to be strength in the nail and the wall that holds up the painting. However, you need to have friction to hold those two components together. Namely, you've got to make sure the nail is a tight squeeze into the wall. Otherwise, the nail will just pull out. Cement does the same thing. It holds the strong components together so that they work together. It holds the aggregate particles together so it forms a strong material. And concrete is very strong, particularly in compressive strength. Now, and that's important. So when concrete breaks, when it cracks, it very rarely breaks through the aggregate. It actually breaks through the cement. So typically, aggregate will make up 70–80% of the volume of the concrete. It actually makes up around 80–90% of the density or the weight of the concrete, because aggregate is denser than cement or water. But you need cement. That's the standard component. You need that to hold these aggregate particles together. So what is concrete? It's not cement, as I said. Cement is the binder that holds the aggregate particles together in one solid shape. And water is needed to react with the cement. And normally it's Portland cement, so it's a hydraulic cement to make it solid. You can make concrete using non-hydraulic cements as well. Lime concrete is a thing, but usually we're using Portland cement. So you can see there in that picture a concrete truck placing concrete on a footpath, and you can see it's all lumpy. It's a mixture of the cement, water, and the aggregate particles all together. So you would have remembered these formulas, and you don't need to know these off by heart, but you would have seen these formulas when we went through cement together. These are the basic hydration reactions that take place for Portland cement. Portland cement has three principal molecules in it: tricalcium silicate, dicalcium silicate, and tricalcium aluminate. And these are the main chemical reactions that take place when it reacts with water. There's about 200 or 300 different reactions for Portland cement, but these are the three main ones. Now, they react with water, and they form these molecules such as calcium sulfate, hydrates, calcium aluminate sulfate hydrates, silica hydrates, and these are the very strong bonds. Now, you'll see that you need quite a bit of water to react with the cement in order to form these strong binding bonds that hold the aggregate particles together in a concrete. What I touched on, but I didn't really go into too much depth when we talked about cement, is the fact that these reactions, they do not happen instantly. They actually, after you mix your concrete and you mix the cement with the water, these reactions will be going on for weeks, even months after you make the concrete. And that's why if you make some concrete, concrete will be much stronger if it's 6 months old than if it's 1 week old. It actually gets stronger with age. So that's called hardening. Hardening is not a case of it going from being liquid or a sludge to solid. It's a case of it going from being a weak solid after it's dried to becoming a strong solid, because these reactions keep on happening. There are still tricalcium, dicalcium silicate and tricalcium aluminate molecules inside the concrete, even though it's dried, that will still want to react with water. And if they find water, they will react and form these strong bonds. So we need to make sure that that water stays inside the concrete, and that's where curing comes in. That's why you'll often see people trying to keep concrete wet even after it's gone solid. They want to keep it wet so there's water for the cement to react with. But as well as these really strong bonds that are created, you'll notice that there's actually a byproduct as well. You've got calcium hydroxides and also entringite. What happens with these? Well, these are gases. They don't actually form any part. They're just wasted chemical molecules there. They will evaporate out of the concrete. They give no strength to the concrete whatsoever, none whatsoever. So what happens to the concrete? Well, if you were to look at concrete under a microscope, you will actually realize that it's like Swiss cheese. It's got lots and lots of microscopic voids inside the concrete, and that's from these gases as well as excess water evaporating from the concrete. Now, that's why the heat of hydration is a little bit of a problem. If you have a lot of heat in the reaction, often what can happen is these gases, they don't escape from the concrete, and they form little air bubbles inside the concrete, and they're microscopic air bubbles. But if you were to look under it in a microscope, it would look a little bit like an Aero chocolate bar. You know those Aero chocolate bars? If you bite into them, they're half chocolate, but most of it's air. They're quite nice, but it's a bit of a rip-off because you're buying mostly air, not chocolate. And it's a very weak chocolate. You can bite down into it very easily. The same is true with concrete. But what you need to know is that this reaction takes place over many weeks, many months. And what you've got to make sure is that the concrete has water that can react with the cement. Because after it dries, if you don't have water that can react with the cement molecules, it will stay as tricalcium silicate. It will stay as dicalcium silicate and tricalcium aluminate. Look at tricalcium aluminate, for example. How many water molecules do you need to bring tricalcium aluminate to calcium aluminate sulfate hydrate, that really strong bond? Well, it's 26 water molecules in the first reaction and 4 water molecules in the second reaction, the secondary reaction. So 30 water molecules in total. Now, what's going to happen if there isn't 30 water molecules? Well, the tricalcium aluminate is going to stay as tricalcium aluminate, or it might only get as far as entringite. Both of these have no strength in and of their own. You've seen cement before when it's dry. It's just powder. It doesn't offer any strength. So remember, with hardening, that is the process of those chemical reactions that I just showed you taking place many weeks and many months after you mix your concrete. It is the hydration reactions happening quite slowly. Hydration does not happen instantly. It happens over several months. And as a result, concrete will get stronger over several months. Now, remember, the finer the cement, the faster the hydration reaction. That's why we talked about the need of cement to be grounded up into really fine particles. But the other thing you've got to remember is that with Portland cement, you've got the different types, type 1, type 2, type 3, and it goes up to type 7, I think. But they will all have different proportions of dicalcium silicate, tricalcium silicate, and tricalcium aluminate. And if you look at that little diagram at the bottom, you've got an increasing, a faster hydration rate as you have a higher proportion of C3S and C3A. So with those things, you need to remember, if you have a concrete and you need it to get strong fast, you want to use a Portland cement in the concrete that has more C3S and C3A than C2S, because that has a faster hydration rate. So remember, hardening is not the same thing as solidifying or setting. So setting is when the concrete sets. It's the process of the concrete drying. Sorry, that's a typo. That should say drying, not strying, whatever that is, and solidifying. So it's going from being a concrete sludge to a solid concrete mass. And this can be a little bit of a problem because you need enough time to place the concrete. Portland cement, the initial part of the hydration reaction takes place very quickly. And so if you just had pure dicalcium silicate, it would dry very quickly, faster than PVC glue. And that's no good for civil engineering. You need time to mix it with the concrete, transport it to site, and then place it and compact it, and then smooth off the surface. So if you remember when we talked about Portland cement, gypsum is added to all Portland cements, just a small amount, about 5%, and this basically acts as a block, and not as the opposite of a catalyst, whatever that is, probably a doggerlist. It just slows down the hydration reaction, and it slows down the setting because of that. And that's very important for transportation. Another thing you can do is you can add an admixture called a retarder. We'll learn more about those when we do concrete technology, but that also can slow down the hydration reaction. Now, unlike setting, which is about a sludge becoming solid, hardening is about a solid becoming stronger. When the concrete first dries, it's a very weak solid, but over time, and I'm talking a period of weeks and months, the concrete will get stronger because the hydration reaction will continue to happen. Cement will continue to react with water and it will form those strong chemical bonds. And the more strong chemical bonds you have in the concrete, the stronger the concrete will become. And so it's very important that you keep the concrete wet. Even after it's become solid, you need to keep it in contact with water so that the cement has water it can react with, because after it's dried, excess water will want to evaporate out of the concrete sludge. And you want to keep water there to react with the cement. So this is called a process. This is a process called curing, and it's about keeping the concrete hydrated. And we'll show more about that in the next lecture. So let's talk about setting. Well, we've already talked about some of the problems if a concrete sets too quickly, namely that you won't have time to place it. If it's not runny enough and it's started to become a thick sludge like honey, by the time you get to the site, you're not going to be able to place it in the formwork, in the mold. Another big problem with rapid setting is something called thermal gradient cracking. Now, this is a problem associated with concretes which also have cements which have high heat of hydration. This was a common problem with lime concrete. So heat of hydration, if you remember correctly, is the heat that comes off the reaction of the hydration reaction. So remember, heat of hydration is different to the reaction rate. The reaction rate is about how fast the hydration takes place. The heat of hydration is about how hot the reaction becomes. Now, why it would matter if with rapid setting is that if the concrete is going solid quickly, but remember, even once it's solidified, the concrete will continue to hydrate, the cement will continue to react with water inside that solid. If there's a high heat of hydration, that heat is going to want to escape from the concrete. And if it's a very new concrete and it hasn't had time to harden, it's going to be a fairly weak concrete too. Now, this is a problem that leads to what we call thermal gradient cracking. So if you're building a really large concrete structure, similar to that concrete wall in the right-hand picture, what's going to happen is you're going to have concrete on the outside, on the surface, reacting. The cement is reacting with the water, and the heat coming from that hydration reaction is going to escape out of the concrete. But really deep inside the wall, a long way from the surface, cement will be reacting with water inside the concrete, and the heat from that reaction will not be able to escape quickly because it's deep in the very heart of the concrete. That is going to lead to cracks forming because in the middle of the wall it's going to be very hot. And I'm not saying super hot. It can go up to about 30-40 degrees Celsius, so you're not going to burn your hand on it. And on the surface, that's going to be the outside temperature. So Today I think the temperature was 21 degrees according to my thermometer. So you're going to have a gradient there of 40 degrees to 21 degrees. Now, obviously, energy wants to dissipate. It wants to move from areas where it's hot to where it's cold. And that energy, if you've got a very steep gradient, that can lead to cracking. Thermal gradient cracks in the concrete, similar to the picture I showed you just before. Deep cracks. And it's very common because also when the concrete is young, it hasn't hardened fully and it's still weak. And that's a real big problem for large structures such as dams. Now, a dam is a very big body of concrete, isn't it? So in the middle of the dam, that concrete is going to be a long way from the surface. So it has no outlet for the concrete to cool and for the heat of hydration to escape. But the surface does, of course. So that creates a big thermal gradient crack in the concrete. You do not want cracks in your concrete of a dam because dams are meant to be waterproof. They're meant to stop water getting through and going downstream. So that's why that's one of the reasons why Saddam Hussein, when he had Mosul Dam built, he purchased pozzolan from New Zealand and he mixed it with the Portland cement to make a Portland pozzolan blend. One of the reasons was it reduced shrinkage. We'll talk about that more later, but that's very important too. You don't want shrinkage cracks forming in your dam. But the other reason is it lowered the heat of hydration, so thermal gradient cracks could not emerge. And it's a very common thing actually for dams. They will often be made out of Portland pozzolan cement for that reason, for reducing thermal gradient cracking and for reducing shrinkage cracking. More on that later on the shrinkage. Another problem with rapid setting is, if you remember, when the reactions are taking place, the hydration reactions, there is a little bit of a byproduct. Calcium hydrates and entringite are part of the final products, and they're gas. And that gas will bubble out of the concrete. It's just going to escape from the concrete. However, if it solidifies and it sets very quickly, it's going to form tiny little bubbles inside the concrete, as I said before in an earlier slide. And that air is not going to give the concrete any strength. It lowers the overall strength of the concrete. So what you're seeing in that picture is, I think it's the Feng Shui Bridge. They built a big motorway bridge in China, and this was back in 2007, I believe. I could have that wrong. But anyway, shortly after building it, a few months after building it, the bridge collapsed and it killed around 40 people. It was a big disaster. But when they examined the concrete and they went up and looked at the concrete, they realized it was really bubbly. It looked like an Aero chocolate bar. If you're not sure what I mean by an Aero chocolate bar, maybe you can buy me an Aero chocolate bar and I can eat it during the tutorial and show you. Just an idea. Just an idea. But yeah, it was bubbly and that had no strength. Air did not give strength to the concrete. So you want the concrete to set reasonably slowly so calcium hydrate bubbles can escape. You're never going to get all of them out. But you want the bulk of them to leave the concrete. But let's talk about hardening now. This is about after the concrete has gone solid. the hydration reactions are still going to be taking place. And this is what happens. This is just an example. After 7 days, the concrete has a strength of 45 megapascals, compressive strength, let's say. At 14 days, it's about 70 megapascals. At 28 days, it's about 10 megapascals. And after 90 days, when it's 3 months old, it's going to be about 100 megapascals in strength. What happens with the concrete is it slowly gets stronger and matures following a logarithmic curve, similar to the one you can see on the right there. You can see number of hours since it was made against compressive strength. And the rule of thumb is that the concrete will have about 90% of its maximum strength after about 90 days. That's a rule of thumb. Now there's a big caveat to this though. You need to make sure the concrete continues to have water on the surface. It needs to stay hydrated. You can't let water evaporate from the concrete through all of the little micro capillaries inside the concrete, because you need that water to react with the cement molecules. If you don't have that, the concrete will not strengthen. And I can show you later when we look at curing what that looks like on a graph. So this is one of the little difficulties with hardening, is if it's slow, the concrete won't get to the strength that is required in time. You'll need to wait longer. And this is a real big problem for civil engineering projects. We want civil engineering projects to be done quickly. There's a lot of time wasted on construction, and there's a lot of economic benefit to be achieved if we can construct the building or the road or the bridge quickly. Now, unfortunately, a lot of time is lost in projects waiting for concrete to harden. Look at this high-rise they're building here. I think it's a high-rise car park. Now, they're building on top of a concrete platform. They're not going to be able to build a new level to that high-rise car park until the concrete underneath it has hardened and reached a strength appropriate for the design. And so that creates delays. The last thing you want in civil engineering is to have lots of workers waiting around twiddling their thumbs, waiting for the concrete to dry. That's not and to harden. That's very expensive. And so that's why project management is a very important field in civil engineering. You're trying to minimize the downtime with construction. I now want to talk to you about workability. Now, this is related to setting. Remember what I said about the concrete going solid, and if it goes solid too quickly, it goes from being a very runny to a very thick, viscous sludge very quickly. You're not going to be able to place the concrete. You're not going to be able to mix it and transport it. You're not going to have the time to do that. Well, that's all related to workability. Those terms I used, ease of mixing, ease of placement, ease of compacting, ease of transporting through a pipeline, those are all given over to the term workability. What do we mean by saying that a concrete is workable? Well, it means it's easy to work with. So workability is really a measure of how viscous a concrete mixture is. So if you're unfamiliar with that term viscous or viscosity, it's basically about how thick or about how runny a liquid is. So something that is very runny would be something like wine. That is a very low viscosity or low viscous liquid. On the other end of the spectrum, honey. Honey is still a liquid, but it's really thick and slow moving. That is a high viscosity liquid. They're both liquids, but in terms of their thickness and ease of moving, that's basically what we mean when we are referring to workability. And so it's basically a combination of how consistent the concrete is, how mobile the concrete is, and how easy it is to compact the concrete. Those are the properties of workability. That's why we need the concrete to be workable. If the concrete is not workable enough, that will mean that it has very high viscosity. It'll be very thick, and that'll mean you won't be able to mix it properly. And it also means you won't be able to place it properly. So remember that the hydration reaction I talked about before with tricalcium silicate, tricalcium aluminate and dicalcium silicate, for that hydration reaction to work, you need to have about 350 mils of water for every kilogram of cement. That's the ratio you need roughly. But if you were to make a concrete with just 350 mils of water for every kilogram of cement, it will be really thick and unworkable. In reality, most concretes will be anywhere between 400 mils to about 1 litre of water for every kilogram of cement, depending on what kind of concrete you're trying to achieve. So that's workability. How do we test workability? Well, I don't know if you've ever seen this, and I don't know if any of you have actually ever made concrete before. Hopefully at the end of this semester, when we're all back at the university and the quarantine with coronavirus is over, we can do this test, we can make concrete together. But the test for testing workability is the slump test. So the slump test is basically where after you've made the concrete mixture, you have this cone, and you can see the cone there. It's a steel cone. It's inverted at the moment, but when it's the right way up with the skinnier neck at the top, you fill it up with concrete, and you compact it, and then you pull the cone up, and the concrete will slump down, and you're basically trying to see how much height of the concrete sandcastle, if you like, is being lost when it slumps down. So the larger the slump, the more workable the concrete is, meaning the more runny it is. Now, it's also a test for making sure that the concrete is well mixed. If it's well mixed, it will form a good castle shape similar to that. If it's not well mixed, it's probably going to crumble into a triangular shape. Now, the slump should be about 20 centimeters for mass concrete. That's concrete that you're pumping through a concrete pump. About 15 centimeters for making a concrete pavement. About 8 centimeters for a concrete beam or columns or walls for a high-rise, and about 5 centimeters or even less for brick mortar if you're making a brick mortar. Now, why is that? Well, imagine if we're making mass concrete and we need to get the concrete through a concrete pump, through a pipeline. Well, obviously the concrete there needs to be very runny, otherwise it's going to block the pipe. For a pavement, you're trying to spread the concrete out over a very large area. Now, obviously, if you don't have if you with all of the excess water that you're adding, remember you only need about 350 mils of water for every kilogram of cement. Well, the excess water that you add in for workability, that's going to evaporate eventually and create voids in the concrete, and that's going to make the concrete weaker. So for very high strength concrete that's required, something like beams or columns in a high-rise building, you need some workability to place it, but you don't want it too high because workability tends to mean that it also has lower strength. So about 8 centimeters is what's expected for beams and columns and walls in a building. Now for brick mortar, that needs to be thick, doesn't it? It needs to be a very thick paste, because you don't want it just spilling off the bricks when you're making a brick wall. So it needs to be 5 centimeters or less. So this is kind of how you do the slump test. You have the cone, and then you start placing concrete inside the cone. Now, what's that man doing there with that steel rod? Well, he's actually compacting the concrete. He's making sure that there's no voids inside the cone. And why is he standing on these little levers on either side of the cone? Well, he's making sure the cone doesn't float up and concrete spills out from underneath. And he basically fills it to 1/3 and then he compacts it. Then he fills it to 2/3 and he compacts it again. And then 3/3 he compacts it right to the top, he compacts it, and then he levels off the top. He makes it smooth on the top, and then he slowly and carefully lifts the cone. Now, when he does that, the concrete is going to slump. And he's going to measure this, he's going to have to use the cone and a steel rod, and then measure the distance between the horizontal steel rod and the concrete. Now, if it's a good slump, it's going to be similar to the slumps on the left there. The one on the second from the left, that's a 0 slump. We probably, unless we're using the concrete as a brick mortar, we need the concrete to be runnier than that. We need it more workable. But if it collapses and it forms a big puddle, that's where you're having segregation. And that means you're going to have a very weak concrete. It still needs to be able to hold its shape. And if it shears off, so it's tall on one side, but it falls down on the other, that means the concrete is not evenly mixed, because you've ended up with 1/2 of the concrete strong and 1/2 of the concrete weak. So you didn't mix it well enough. So if it collapses or it shears, that means you need to go back and fix your concrete before you can use it. Now, I've placed a video of a slump test online. You can go to the link on the Moodle page and you can see a slump test. And we will do a slump test together in the lab when we get back to the university. Now, There is another way of measuring workability, and that's called the Kelly-Bell test. Normally, the slump test is the most common test we use for workability, but the Kelly-Bell test is a little bit different, and it does have some benefits to it. So with the slump test, you're looking to see how much the concrete will slump. With the Kelly-Bell test, what you're doing is you're basically inverting that. You're assuming that the concrete is at the bottom and the apparatus is on top. And the apparatus is a big mallet, if you like, a big heavy weight. And you lift this weight up to, I think, 15 centimeters is the standard apparatus, and you let it go. And you try to measure how much the big heavy iron head will sink into the concrete. Now, if it's very runny, it's going to have a big penetration. If it's very stiff and thick and would have a low slump, low workability, then it's going to have a small penetration. Now, I've put a video of the Kelly-Bell test on Moodle for you to look at. Why would we use the Kelly-Bell test rather than the slump test? Well, it does have a couple of advantages, the Kelly-Bell test. One of the advantages of the Kelly-Bell test is that with the slump test, you should test the concrete before the concrete is placed. And that's common practice, and most contractors and construction people know that. You test the concrete to make sure it's workable enough, and then you place it. If it wasn't workable enough, then you're going to have trouble compacting it. Now, sometimes you get a moron who works at the construction site, and he won't do the slump test, and he will pour the concrete before you can test it for workability. This actually happened for me in my early career as a civil engineer. I was working at for a dam company in New Zealand, and what we were doing were we were building a concrete wall close to the power station. Now, I was the civil engineer who had designed the wall, and someone else was constructing the wall. Now, I had to go to site at various stages of the wall's construction and sign it off and approve it and say, you can continue. One of those phases was actually the pouring of the concrete. And what needed to happen was I needed to be there. I needed to check the concrete mixture and do a slump test and make sure that it was workable enough, and then say, okay, you can pour the concrete. If it wasn't workable enough, they wouldn't have been able to compact it, and that would have meant there would have been voids inside the wall, and it would have led to honeycombing. More on that later. Now, I got to the site, and the moron who was in charge of the construction, he had already poured the concrete. And so I needed to quickly find a way to test the workability of the concrete that had already been poured. Now, fortunately, there was a Kelly-Bell test apparatus at the site, and I was able to go to the top of the wall and use the Kelly-Bell test to check the workability this way by seeing how much the bell penetrated into the concrete, and fortunately the concrete was fine. Now, the other advantage the Kelly-Bell test has over a slump test is that you can test the concrete in lots of different locations. You just pick up the apparatus and move it around. And if the concrete is consistent, meaning that it's well mixed and the aggregate and cement and water ratios are the same throughout the concrete, The penetration will be the same wherever you go. If there's variation in the penetration, that's a clear sign that actually the concrete hasn't been mixed well enough. So that's another advantage of the Kelly-Bell test. But as I said, for the most part in industry, we use the slump test. But there are a couple of advantages for the Kelly-Bell test. Sometimes we will use that. So what are some of the factors which affect workability, which will determine whether your concrete is very stiff or if it's very runny? Well, one of the big ones is actually the grading of the aggregate. Remember how I said it was very important that the aggregate for concrete is very well graded or gap graded, and that's needed for strength as well as economy. Well, the other reason is because of workability. If it's poorly graded, meaning that most of the aggregate particles are the same size, the slump will collapse, and that will lead to a much weaker concrete. It also will lead to segregation, which we will talk about in the next slide. So often what happens is if you do a slump test and the slump collapses, one of the first things you do is you add fine aggregate, you add sand, and that's to improve the grading, to make it more better graded, more well graded. The other factor is water. If you don't have enough water in the concrete mixture, the slump will be stiff. Likewise, if you have too much water, the slump will be too runny. And so you've got to get the right balance to have the right slump that you need, depending on what the concrete's being used for. Now that is pretty clear. More water makes it runnier, less water makes it stiffer, just like baking a cake. But the other factor which affects workability is the process of setting. Now remember what I said, the hydration reaction between cement and water, it starts very quickly with Portland cement. And so it will begin to set, it will slowly go stiff even after you first mixed it. And so it can already, if you mix a concrete at a concrete factory and you do a slump test of it at the concrete factory and the slump is 15-20 centimeters, you could then put the concrete in a concrete truck, and by the time the concrete has arrived at the site on the other side of town, you do another slump test, and now the slump is only 10 centimeters. What happened? Well, the hydration reaction was already taking place and the concrete was already beginning to set. So that can affect workability time after mixing because of the setting. So what do you do if you test the concrete with a slump test and you don't get the slump you need? Well, we're going to do this together when we make concrete later in the semester when we get back to the university. But you've got to remember that making concrete is similar to baking a cake in that it's not an exact science. When you bake a cake, you follow a recipe, don't you, that you got offline or from a recipe book or one that your grandmother gave you. But then you test the batter, you test the mixture, you take a taste, and then you say, well, actually, it needs a little bit more milk. It might need another egg. It needs a little bit more sugar. And you're just trying to get the balance perfectly right. And then you bake the cake. Well, it's the same with concrete. We will be given a recipe for concrete, which we will follow. We will mix the aggregate and cement and water according to the ratios given. But then we will do a test. We will do a slump test. Now, If the slump is too stiff for what we want the concrete to be, we've got a couple of options. One thing we can do is we can add water. Now, that's a little bit of a problem though. If we add more water, remember this is excess water that is not needed to react with the cement. Remember, you only need 350 mils of water to react with 1 kilogram of cement. So if we're adding excess water, that water will eventually evaporate when the concrete dries, and that's going to leave voids inside the concrete, which will make the concrete weaker. What you've got to remember is that concrete that has a high water ratio will be a weaker concrete. So another way we can soften and make the slump more runny without weakening the concrete is we can add a retarder admixture. What's a retarder? Well, I like to think of a retarder as a laxative. What's a laxative? Well, when you're constipated because you haven't been eating well or drinking enough water, and you're really stiff downstairs and you need to go to the toilet but you can't, what you can do is you can take a laxative, and that will make you run like the Ganges River, and so you can relieve yourself in the bathroom. That's what a retarder is. A retarder is a chemical that you add to the concrete that acts like a laxative. It makes the concrete runnier. So what do you do if the slump is too runny? What if you need to reduce the slump? Well, one of the first things you can do is you can add sand. Remember, if you've got excess water, sand will basically hold that water on the surface area, and so basically it would make it stiffer. Just like if you've got, if you're trying to make a cake and you you're mixing milk and flour together and it's too runny, you add more flour. Of course, you've got to make sure that the sand is dry. If you're going to add wet sand, you're only going to make the slump runnier. Now, another thing you could do is you could add a water-reducing admixture. This is a chemical which acts as a dehydrator. It basically bubbles off the excess water, and that'll make the slump stiffer. But the easiest thing to do is to just wait for it to harden a little. It will set, the slump will go stiffer in time, so just wait 10, 15, 20 minutes or even an hour and it'll go stiffer. So normally the biggest issue we have in civil engineering is that the slump is too stiff. We're not too worried usually about the slump being too runny, unless it's so runny that the slump collapses, which is a weak concrete. So now I want to talk to you about segregation. Now, what does segregation mean? Well, segregation is a word which means the separation of things or people that are different. The word is most commonly used in the English language to describe segregation between races. It was a word used in South Africa until the 1990s, and a word used in the United States of America until about the 1960s to describe the segregation of the races. Blacks and whites were not allowed to mix. That was against the law in many parts of the USA and South Africa. And so you had situations such as even water fountains. They weren't allowed to share water fountains, and it all stemmed from racism, basically. Well, segregation can occur in civil engineering too, but don't worry, it's not racist. When we talk about segregation in concrete, what we mean is that there is a separation of the ingredients of concrete which are different, namely the aggregate and the cement and water. When we mix it all together, there should be an even distribution of aggregate particles throughout the concrete mixture. But segregation occurs when aggregate, particularly the large aggregate particles, which have a high density compared with the cement and water, they will sink to the bottom of the concrete, and the cement and water, which is quite light and has low density, that will float to the top. And so you will end up with a concrete that has very low consistency. One part of the concrete will have a lot of aggregate and another part will have very little aggregate, and that makes the concrete weaker. It's a real big problem, and the way you know you've got segregation is when you do the slump test and the slump collapses. It forms a big puddle. That's a clear sign you've got segregation, and you've got to fix the concrete before you can use it. So this is basically a diagram showing you what happens. What we have here is we have large aggregate particles, and we also have a very large we have cement and water mixed together. Now the aggregate, particularly which has very high density, but also some of the cement, that will sink to the bottom, whereas the water and aggregate particles which are suspended by water-rich bubbles or pockets on the surface of the aggregate will float to the top, and you will end up with a very small film of water on top called the latents or surface latents. And so you're going to end up with a lot of aggregate on the bottom and a lot of cement and water paste on top, a weak concrete. And this is what it looks like in actual concrete. So we can see concrete on the left there, that's dried, and you can see that segregation has happened. All the large, dense, coarse aggregate particles have floated to the top, and to the bottom have sunk to the bottom, whereas the light cement and water particles form a paste which stays on the top. And on the right you can see a core sample, and you can clearly see that it's not consistent. There's very large aggregate particles near the bottom, but right at the top you have very little in the way of aggregate particles. That is going to be a weak concrete. Both of these are weak concretes because there hasn't been mixing. We want all of the mixture, all of the ingredients of the concrete mixed together like a cocktail tutti frutti. That's how we get the best strength concrete. So how do we avoid segregation? Well, one of the things is we've got to make sure the slump is not too high. If we have a slump which is a very big slump, then it's going to be overly runny and it's going to lead to segregation. So that's the collapsed slump that I was talking about. Now, this can be avoided by making sure that the aggregate is well graded. Remember how important a well-graded aggregate is for the strength of the concrete and the economy? Well, a lot of it comes down to segregation. You've got to make sure that the concrete doesn't segregate, and that's ensured by making sure the aggregate is well graded or gap graded, as the case may be. So you need to have enough sand particles to fill the voids between the coarse aggregate particles. And another important thing about segregation and how to avoid it is you don't drop the concrete from a great height. If you drop the concrete from a high height, what will happen is basically the concrete will splatter and water will bounce out of the puddle, and the rocks and the coarse aggregate particles will form a big pile in the middle, and that causes segregation. So we've got an example here on the right of a concrete column. Now, the correct way to pour a concrete column is with a pipe or funnel called a hopper. And what that does is you place the concrete in there and it slowly moves the concrete down the funnel, and then then it falls out at the very bottom. And that way you're ensuring segregation doesn't happen. That's the right way to fill a concrete column mould. The wrong way is shown on the right, where you're pouring it from a great height. When what's going to happen is it's going to come down with a big bang, a big acceleration, and all of the large aggregate particles are going to sink to the bottom, and that's going to weaken the concrete. It causes segregation. So the rule of thumb in construction with concrete is you never drop the concrete from a height higher than 1 meter. If you're dropping it from a height higher than 1 meter, you're going to start having segregation. So one kind of segregation which is very common, or you'll see this with all segregation, is something that we call bleeding. Now, bleeding is where basically you see puddles of water forming on the surface of the concrete. Basically, excess water is basically dropping out of the concrete. So what you see down here is actually a slump test, and it's a collapsed slump. That's segregation. You can see a pile of rocks, aggregate particles in the middle, and all around the edge you can see a big grey puddle of cement water. That's going to be a very weak concrete. When the water is bleeding out of the concrete like that, it leads to a weak concrete, because you're going to end up with it not being consistent. It also means that potentially a lot of the cement, which is holding the aggregate together, is going to bleed out with the water. There may not be enough water to react with the cement, and also the coarse aggregate is not going to fit together like a tight matrix. It's going to lead to a very weak concrete. So this is what bleeding looks like. You can see here that they've made a concrete surface here. This is a picture I took in Oman when I lived there. And Oman, it wasn't raining. They haven't hosed it down or anything. You can see on the concrete surface, and this is wet concrete that they've just placed, there's a small film of water forming on the surface, a small puddle. That is water bleeding out of the concrete. That's going to weaken the concrete. They've probably added too much water to the concrete mixture, and it's created this bleeding or this minor segregation. So that's another thing we want to avoid. And so preventing bleeding is similar to preventing regular segregation. You do not drop the concrete from a great height. Now, increasingly this has become easier because we now use concrete pumps, similar to the one on the picture on the right. And you can see one of the great things about concrete pumps is accessibility. Places which were a little bit hard to reach from the roadside and it was hard to get the concrete to, you can now put the pipe right above where it needs to pour. And so you never need to drop it from a height. Concrete pumps are great for preventing segregation and bleeding. The other thing that can lead to bleeding is you don't have the correct cement-water ratio. You have too much water for cement, so you probably need to add a bit more cement if it's bleeding, or reduce the water somehow. But the other thing that causes bleeding is over-vibration. How do we compact concrete? Well, one of the key ways we often compact concrete is we will vibrate it. We will place a vibrating rod inside the concrete that's been poured, and that will shake the concrete so that it falls down into the mold, and that will take away all of the voids. And so we use vibrators a lot in construction engineering for concrete technology. It's for compacting the concrete, it's for pounding the concrete into the mold. Now, if you vibrate for too deeply and the vibrator setting is too high, or you vibrate for too long, then you're going to start bleeding. That's a problem with vibrators. So you've got to use the vibrator wisely. If it starts to bleed, you take the vibrator out. Now, with compaction, the thing that you use the vibrator to achieve, if you don't compact the concrete correctly, you're going to end up with voids inside the concrete. And those voids will mean that the concrete is weaker, because basically they're air voids which add no strength to the concrete. And you can often see these voids in a phenomenon known as honeycombing. This is where the voids are seen on the surface of the concrete after you take away the mold face or of the formwork. And so you can see on both those pictures honeycombing. You've probably seen honeycombing around the place at various places where concrete has been used to make structures, and it's very bad. Normally, if there's honeycombing to that extent, the civil engineer shouldn't approve it, and it needs to be redone, unless, of course, it's not actually structurally important to the integrity of the infrastructure. Now, how do you avoid honeycombing? Well, you've got to make sure you compact it well to get rid of all of those air voids. Now, that's one of the reasons why you need to have a workable concrete. If the slump is too small and the concrete is too thick, you're not going to be able to compact it fully, and you're going to end up with voids. It's also important to use good compacting technology like vibrators. It's also important that you have enough fine aggregate. If you don't have enough fine aggregate in the concrete, then basically you're just going to start bleeding, and the water cement paste will separate from and segregate from the coarse aggregate, and you end up with honeycombing. So those are things to avoid. So I think that's going to be enough for this lecture. Next lecture, we're going to be talking a little bit about placing concrete and also about treating solidified set concrete with curing. So we mentioned the term curing before. Join me for the next lecture when we talk about the process of curing and what that does. Thank you and goodbye.